Okay, I think we can start our today's lecture. In our today's lecture, we want to discuss about big data recommendations. Okay, big data recommendations. I think still we are few students here. Just 18 students join. I don't know. What about others? So many of you already familiar with our recommendation systems. That means we have to develop a recommender engine, and that will recommend the similar items or likely items. Like if we can think about, that is the user. This one is the user, and user maybe search one of the items here. Any of the items that search. Maybe it can be news items, it can be websites, it can be any products. Uh, then based on this search, what usually we want to find out, what we want to provide him, that is provide some recommendations. Okay, the similar items or that is similar types of maybe products, similar types of blogs, similar types of websites. Okay, that's the recommendation system. Usually, recommendation system, the application of recommendation system is a variety of recommendations. You can find out the recommendations in YouTube. That is, if you watch one of the movie, usually YouTube suggests the movie of same genre maybe. So this is one type of recommendation. If you search one book in Amazon, then it will also recommend you some similar kind of maybe books, or we can say that is maybe previously some of the user already bought that book, and together with that user also bought some other books. So it will recommend you the same thing. That means maybe if you bought one book, based on the purchase history, it will recommend that these other books also maybe bought by several other users also. So this is actually the recommendation system. But how to develop the recommendation systems, and what are the types, and specifically what's the problem in big data recommendation systems, uh, and how to deal with that. So that's we will learn in our today's lecture. Uh, so the formal definition, or we can say that the formal problem in recommendation system is, if we can think about like X is a set of customers and S is a set of items. Uh, so these customers and these are the items. So what usually we want to find out? We want to find out utility function. Mathematically, we can call it the utility function. Based on this X and X, we want to find out the corresponding rating for that. Okay, maybe we can say that is X is one of the user A, and S is one of the item, maybe the book Harry Potter one. Uh, so what will be the that is the predicted rating of that user on that book. So usually we want to find out that, and based on the rating, maybe you can say if the predicted rating is high, then then we can recommend that to that user. If the predicted rating is low, nearly zero maybe, so no need to recommend that book to that user. Okay, so that means we want to find out actually utility function based on user and the items. So uh, uh, so that's the problem we want to solve in recommendation systems. Like here is an utility matrix. Okay, utility matrix we can see there is the Alice, Bob, Carol, and David. Uh, so those are the users. Okay, those are the users. Then the customers. Those are the customers. And uh, and several movies are there. So these are the movies. Okay, these are the movies. Like here is um, Avatar, and then LOTR and Matrix and Pirates. Uh, and we can see that the rating of Alice to Avatar is 1. The rating Alice to Matrix is zero point 0.2, and then there is Bob rate the LOTR is zero point 0.5, and Bob rate the Pirates is 0.3. Similarly, Carol rate the Avatar is zero point 0.2, and Carol Matrix rating is 1. David's Pirates rating is 0.4. So these are the ratings. Now, what usually we want to do? Uh, we can see that maybe we can see we can see that there is the Bob rating for Pirates is zero point 0.3, and Bob rating for David the David's rating for Pirates is zero point 0.4. Uh, but we want to find out that that is whether Alice will like the Pirates movie or not. Okay, so that means we want to predict the rating of the Alice in Pirates movie. So this is the in recommendation systems. Usually we want to find out that the Alice the the predicted ratings of Alice in Pirates movie. Maybe we can say if that one is like maybe zero point 0.6 or something 0.6, then maybe we can recommend that movie to Alice. Okay, so how can we predict that? How can we find out this value, that is the predicted value? So that's the issue in recommendation systems. But um, we can do it in several ways, and we will discuss about that. Uh, then the key problem here is gathering known rating for the matrix. That means what's in recommendation system usually we want to do, that is the gather the ratings. Without those ratings, maybe you can say without these ratings, uh, we cannot find out the predicted rating for uh, the Alice in Pirates. Okay, so that's why the gathering known ratings for metrics, that's important, and then extrapolate unknown ratings from the known ones. Okay, so this is another problem, that how can we find out or how can we predict the unknown ratings uh, based on the known ones. And another thing is evaluating the extrapolation method. Evaluating the extrapolation method. That means, okay, we will find out the value that is the predicted value, but how can we measure the performance? That whether this prediction is right or wrong. Okay, so this is the challenge in our recommendation systems. Uh, so gathering ratings, it can be explicit, it can be implicit. Okay, the explicit is you can ask the people to rate the items. Um, uh, yes, but sometimes it doesn't fit well for many of the applications. Okay, so maybe many of the people will not actually rate. Usually, in case of our maybe database, in case of our purchase history, many of us actually don't like to rate, or we can say don't like to make a comments even. Yeah? Uh, but we can find out that is ask the people for rating or comments on it, and based on the ratings or based on the comments, we can find out maybe find out the ratings. And another thing is implicit, that is learn ratings from user actions. if a user purchases an item, it means that maybe that user like that item. If the user purchases that item again and again, maybe he liked that item very much. Okay, so that's called the implicit. And so based on the behavior and actions, we can also find out those kind of ratings. Okay, and for extrapolation, yeah, there are several things to do here. That is the extrapolation. So you want to predict based on several things. Okay, what you can do that means you can apply maybe some form of machine learning algorithms there, some form of predictions to predict something. It can be a regression problem. If you can formulate that problem as a regression problem, and then they find out uh, the the values, specifically the parameters of the regression problem. If we think about if we consider those are just a linear regression, then you need to find out uh, specifically the m that is called slope and also the y-intercept. Okay, if you consider just only a line y equal mx plus c. Okay, so we need to learn the M and C. So for that, maybe there are several algorithms already, or we can say optimization theoretic solution already we have to find out those kind of M and C. Uh, then if we get the M and C, we can easily predict the unknown predicted values. Okay. But what are the key problems here? The key problem is cholestat problem, usually we call it. That is, new items have no ratings. So if an item is just only introduced here, maybe you will not get the ratings for that. Okay, so that's one of the key problem. And new users have no history. Okay, if you want to recommend some products to a user, that's maybe just newly joined user. Then again, the newly joined user, they don't have any history. So that's another big problem, because if we try to find out there is something for him, but we don't know uh, the mind or the behavior or the liking of that new user. So that's problematic in extrapolating. uh, so those are the key problem. Specifically, the recommender systems, we have three types of recommender systems. Okay, one is called the content-based recommendation system. Another one is collaborative filtering-based recommender system, and another one is called latent factor-based recommendation system. We will cover the content-based and collaborative filtering in this lecture. Then, what is content-based recommender systems? So here, content-based, that means based on the content similarity, based on the content similarity, based on the content features. You want to recommend uh, some other contents to a specific user, okay, a specific customer. So that's the content-based recommendation. The main idea is recommend items to a customer X similar to the previous items are rated highly by X. Okay. So that means you have to find the similar items, the customer ratings, the previously rated highly by that customer X. Here example is movie recommendation. So recommend movies with same actors, maybe same director, or maybe same genre, okay, to the specific customer X. So this is based on what? Based on the similarity of the items and based on the ratings previously rated by uh, that um, that customer. Um, and another example, maybe website, blogs, and news recommend the other site with similar content. Okay, similar content. If the content is similar, then recommend that also to the customer. So what's the plan of action here? What you have to do at first? You have to this is, we can say, that is uh, that is user or customer. Uh, so customer likes these things. Maybe you can say one circle and one triangle. Maybe you can say customer likes there's one circle, there is a red circle, and here is the one triangle. So these are the items customer liked previously. Okay. Then what we have to do, we have to find out the item profile, or we can say that is the actually item features. Okay? Features, item features. Uh, so build the item profile. That means you have to find out what you have to find out the feature vector for each and every item. Let's say we build the feature vector like this customer like actually the red color, um, and we can see these two. One is circle and another is a triangle. So that means we can see there is these are the item profiles. Okay, item profile. That is the features of those items. Then we have to find out also the user profile. That is, okay, user actually like the red color, user like the circle, and user like the triangles. Okay, so those are user profile. Then match uh, between those. That means we can say that uh, there here are some items. Then we have to find out that is the maybe red color. So here is the red. This one is red. And then we can say the circles and triangles. So here is the circle, and these are not the circles. Okay, these are not the circles. Uh, so that means we should not recommend this item and this item, but we can recommend these two items. We can recommend these two items, though actually those are not the same. Okay, not the same. That means based on some sort of similarity. The similarity, that means similarity in red and similarity in circle. So we can recommend these two items to the that is our user or customer. Uh, so that's usually we do in our content-based recommendation systems. So how to generate the item profile? In item profile, maybe you can create the vector. Like for the case of the movies, you have to generate a feature vector using the author, the title, the actor, and director, like this. For the case of the text, as the set of important words in document, there are several actually feature extraction methods in text also. We know about the TF-IDF vectorization. Okay, TF-IDF vectorization. We know about the there is backup words. We know about our word to vec. We know about our word embeddings. Okay, so all those are actually feature extraction methods, and we can extract features from the documents or maybe uh, from the comments. Okay. Uh, so here, one thing for the text, I think the TF-ITF vectorization is very familiar. Many of you already know about it. That is the TF and ITF. So we have to find out this actually. At first, we need to compute the TF, that is term uh, uh, frequency and inverse document frequency. What's the term frequency? It means frequency of an item, that is a frequency of a term, like feature I in the doc I, maybe that is the J. So term, maybe if you are processing the document, and on the document the term Apple is there. Okay, Apple, term Apple, and and you are processing many documents. Okay, many documents, or maybe many comments, many reviews. Okay, Apple. Uh, so the term frequency here, term frequency means the frequency of this term, that is Apple, in the document J. Okay, maybe document we have many, but currently we are focusing on document one. So document one, document two, maybe we have many. Okay, document three, maybe we have thousands of documents. Okay, thousands of documents. Then we are currently focusing on document one, and in the document one, we are trying to find out the frequency of the term Apple. Okay, so here this is frequency of the term Apple here, and then the frequency of the term Apple in maybe on other, the maximum of that, the maximum times. Maybe in first document, uh, the term Apple appears maybe 5 times, but this apple, maybe in other documents, the maximum apple terms appeared on those documents maybe 25 times. Okay, so this is the term frequency for this apple. And then we have to think about there is the inverse document frequency also. There is number of documents that mention the term I, okay, and the total number of documents. So this is called the IDF of I, okay, I, that is the term apple, IDF of apple, IDF of apple. It will be log of the n is the total number of documents. In this case, we can see we have total 1000 documents. So here you can consider this one is 1000, and then divided by, that is ni, this is ni is the number of docs that mention term I. Maybe out of our 1000 documents, only 10 documents mention the terms. Okay, so this is inverse document frequency, log of n by log of n by, this is, we have to take the log here. Okay. Then this is called the TF-IDF score, actually weighted value of term frequency and inverse document frequency. Okay, inverse document frequency. So you have to find out that there is TF-IDF for each and every term, and for each and every document also. Okay, every term and every document. That's why here WIJ, the I is the term and J is the document. So WIJ, that is for a given term like apple. I is apple. Apple, and J is maybe you can say the document one, and the value for that we will get here. Okay, in this way, maybe we will get for each and every document we will get the that is the TF-IDF for each and every term. Then that will be our feature vector. Okay, that will be our feature vector. There are some other ways to find out actually uh, 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 the feature values for the documents, for the comments. Okay, so we can apply any of those. Now user profiles and predictions. Okay, for the user profile, the possibilities is weighted average rated item profiles. Okay, that is weighted average of rated item profiles. Uh, Here the variation weight by difference from the average rating for items. Okay. So here the weighted average of rated item profiles, we can find out that those are our as user profiles. Um, Now the prediction, usually for the prediction, what we can use some sort of maybe the function that is called the similarity function. Like you can apply the cosine similarity. I think many of you already know about the cosine similarity, how to find out the cosine similarity. If we want to find out the cosine similarity between two vector like A and this vector, like we have maybe 2, 3, and 5. This is one vector, and we want to find out there is another vector like B, and this vector just maybe 1, 2, and maybe 1. So this is another vector. And now we want to find out the cosine similarity between these two vectors, uh, specifically the angle between these two vectors. Then what we have to do? We have to that is find out the dot product of A and B. Okay, dot product of A and B. That is this is the case X and I. Considering this one is X and this one is I. This one is I. Uh, so the cosine similarity, it will be that is the dot product between these two vectors. So if we try to find out the dot product, it will be 2 times 1 plus then 3 times 2, and then plus of uh, 5 times 1, 5 times 1, and then divide by this is norm. there is or length of vector A and length of vector B, or length of vector X and length of vector I. There is the Euclidean norm of vector X and Euclidean norm of vector I. So the vector I, the elements are, these are the elements. The Euclidean norm, it will be the square root of the summation of squares of each and every term. So that is 2 square, 3 square, and then plus 5 square. Okay. Uh, and also we have to multiply this one by the I, the length of I. So length is square root of 1 square plus 2 square plus 1 square. Okay. Okay. So if we do the math, then we will get the cosine similarity. Okay, cosine similarity between these two vectors. So easily we get the result within 0 to 1. Okay, within 0 to 1. So 1 means highly similar, and 0 means that is they have low similarity. So in that case, we can say there is specifically it mentions the angles. So if we consider this is just our x and this is our I, so consider this is our I. So these two vectors we have the theta. Okay, the dissimilarity means the theta is greater, and similarity means they are just, maybe you can say the one means they are on the same line. Okay, the vector is, two vectors are just superimposed. Uh, so this is the prediction heuristic. That means we can find out the similar items based on the cosine similarity, or maybe you can say some other metrics also we have. And then what's the pros and cons of our content-based approach? So in content-based approach, no need of data on other users. Okay, because in content-based user, content-based uh, uh, method, content-based recommendation systems, we don't need the data on other users, because what other users like or maybe don't like, actually we didn't consider those things in content-based recommendation systems. And able to recommend the users with a unique taste. Okay, that means we can say it's possible in content-based, because based on the users liking, usually we recommend the items. So able to recommend new one, maybe unpopular items also. Okay, so maybe you can say sometimes maybe the new items will be there, and unpopular items will be there, but no need of others rating on it. So what we need, just maybe we need to find out the feature of the items, and based on those features we have to find out the similar items, and based on the similarity we will recommend the similar items to the users. Maybe he liked those items previously. Okay, so that's why even though no uh, that is the new item, we can apply the recommendation, content-based recommendation systems on it, and able to provide the explanation. That means it is easy to explain uh, why this item is recommending, because based on the similarity, big similar item, that's why we are recommending. Then what's the cons here? The cons here is finding the appropriate feature is hard. Okay, that means we need to find out the similar items. So similar items means we have to find out the features of each and every items. The finding out the feature is difficult. Okay, so that's why this is one of the cons of content-based recommendation systems. And recommendation of new users, again this is also problematic. That is, if the user is new, we don't have the data for his or her likings. Okay, uh, so that's why again content-based recommendation is on that case it is difficult. And over specialization. Uh, what does it mean? Never recommend items outside users' content profile. Maybe we can say uh, we only can recommend the items that previously liked by that user. Maybe some other items are also interesting, but usually we didn't we don't consider those items for recommending in content-based recommendation systems. So now I want to show here that is the method of uh, finding the content based recommendation systems. Like one example in this case, if you can think about that, these are the users and these are the features and these are the movies for that. Okay. Uh, what we have to do, we have to find out that is the feature values for each and every movie. Maybe if you consider about we have two features like X1 and X2. X1 represents how much romantic the movie is, and uh, that is and X2 contains that is maybe how much action contains on that movie. Uh, so, like the man from nowhere, on that case, in this movie, this is kind of the romantic movie. There is no action, and then Uchi is another movie, and on that case, maybe you can see is the romantic, highly romantic, but there are just a little actions on it, and the good, the bad, and the weird. On that case, it is also kind of romantic movie, but there is no action. Doomsday book, on that case, maybe it is not romantic. The romance is very little, but it's the full of actions. And the white, the melody of cars, on that case we can see also there is no romance in that movie, but uh, this is the lots of actions are there. Okay, that is the point 9. So it means we know the feature values, we know the content feature values of each and every movie. And now maybe what we want to do, we want to find out that is for the moon, whether we recommend some contents or not. Like moon already have the ratings on the man nowhere. Okay, and also moon already watch the good, the bad, and the weird, and the rating for that is 4. And moon also has the ratings in doomsday book and the white, the melody of the cars. So those are just maybe the 0 rating. Okay, so that means uh, actually moonlight the movie, the man from the nowhere, this movie, and also the good, the bad, and the weird, that movie here is the 4. And don't like the movie, these two movies don't like. uh, what we want to do, we want to predict that is whether we uh, will recommend this movie, that is Uchi, to moon or not. Okay, so whether we want to uh, actually recommend this movie, that is Uchi, to moon or not. Okay, so that's we want to find out. um, there are several approaches, but the easy approach is at first we need to find out the similarity. So that means we need to find out maybe k number of similar items, that like you can say the k number of similar items of this movie. So we know the features, that is we know the feature here, these are the feature values. Then what we want to do, we want to find out the similar movies, like here. But we only consider k number of similar movies, maybe k equal 2 on that. Let's consider that k equal 2. It's like the KNN. I think many of you already familiar with the K nearest neighbor. It is similar to that. That is, we want to find out the K likely movies or K similar movies, K number of similar movies. Here, consider the K equal 2, or maybe consider the K equal 3, uh, based on your that is choice. So let's say K equal 2. So we want to find out the two similar movies. Okay, similar movies. So here we can see uh, we need to find out the similarity, measure the similarity. That is, maybe you can say we want to apply the cosine similarity for that. The cosine similarity. If we consider that this movie is actually the movie A, and this is movie B, and this is the C, and this is D, and this is E. Okay, so what we have to do, we have to find out the cosine similarity between the B and A. So the B, we want to find out whether we will recommend B to moon or not. Okay, so cosine similarity between B and A, we have to find out, and then we have to find out the cosine similarity between B and maybe C. We have to find out the cosine similarity between what, between B and D, and then we have to find out the cosine similarity between B and E. Okay, that is those. These are the movies uh, watched previously by Moon. Okay, so we just considered those movies uh, previously watched by Moon. Okay, and then we can see here the cosine similarity. We will find out the cosine similarity among these movies. So let's say the cosine similarity, I have already shown the how to determine the cosine similarity. I think you will get you can find out the cosine similarity. So maybe B and C, the cosine similarity, just assume that the cosine similarity B and C, it is 0.8 maybe, and then B and A maybe 0.9, and then B and D is cosine similarity 0. Just maybe 0.1, and the cosine similarity between B and E may be 0. 0. Just maybe just 1. Okay. Then based on the similarity, we have to find out that is the nearest neighbor. Okay, we can say that is two nearest neighbor we want to find out. So that means based on the similarity, the higher the similarity, those are usually we considered as our neighbor of B. So on that case, this is the highest value, okay, because the best we have to sort the similarity, and we can see this is the highest similar. So that means A uh, has the highest similar value with B. Similarly, we have to find out another one because K we considered 2. So this one is also another one. So that is C. So B and C. So we can say B and C. Those are actually the similar. B and C. Okay. So that means B and C and B and A. So B and A, B and A. Those are actually similar to B. So now what we have to do as we consider K. Uh, so now we want to find out the rating of Uchi here. This is we want to predict the rating. We want to predict the rating here. Uh, on that case, the rating can be, we can say, uh, the average value of these two. So average value, if we consider just the average, then 5 plus the 5 plus 4, okay, 5 plus 4, there is a moon's rating on A is 5, and moon's rating on C is 4. Then 5 plus 4 divided by divided by 2. Uh, so this will provide us this 5 plus 4 is 9. 9 by 2 is what? 9 by 2 is 4.5. Okay, 4.5. 4.5. Okay, so that this is one kind of prediction. This can be 4.5, but we can also think about that weighted similarity for the weighted value. So in case of the weighted value, what we have to do, that is this 5, uh, we have to multiply this one by the similarity value. Okay, so 5. First, the similarity value uh, of this 5 is on A. Okay, so what's the similarity between B and A is 0.9. So here is 0.9, 0.9, and then uh, plus of here we can see uh, that is 4 times. What's the similarity value of our C here? The BC it is 0.8, so here is the 0.8. Okay, 0.8, and then we have to divide this one by the summation of the similarity values. Okay, summation of the similarity, that is 0.1, sorry, 0.9 plus of 0.8, 0.8. Then we will get the value. Okay, so that value is usually called, that value is the weighted value. Okay, so that means we can find out, uh, we can predict the value. Sorry, we can predict the value, or we can say rating of Uchi here, in 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 case of our user moon. Similarly, we can also find out for the Kim, for the Lee, and for the Reem, and maybe for the Lee. Okay, so we can find out those values also. So this is called the content-based recommendation system. But as I already mentioned, that actually we have sophisticated method. Not only this based on the similarity. Okay, we have the sophisticated method for that. If we consider this one, if we can formulate this problem as a regression problem, then we can think about like, we can think about what will be the predicted value for this, based on our regression problem. Uh, so so for that case, maybe you can see, for we have the feature values, like this is Uchi. Okay, we see the feature values. Um, we can think of x1 and x2 here, x1 and x2, x1 and x2. What's the value of x1? X1 is, we can say so 1.0, and x2 is 0.01. And we can consider the feature values of XOC, considering uh, uh, that is adding another, uh, we can say it is the uh, uh, intercept feature. Okay, intercept feature, because we know that there is y equal mx plus c. The c is intercept. Okay, so not only the feature, but we have to consider that is the c also. And that c value, it is you can consider as a feature, and that the value is always one. Okay, so we can construct the feature vector for the Uchi. Now, if we can think about like this problem is actually the our regression problem. So regression problem, it means uh, we can predict the value, that is the predicted score y, uh, using maybe the multilinear regression, uh, and that is m and x plus c. But we can see that we have two features. So x is just one, not one, it is actually two. And here is our m. So m is our, we can say, that is actually the coefficient of each and every features. On that case, we can think about like, we have two features. On that case, one is m1 x1, and then another one is m2, maybe x2, and then plus of c. Okay, plus of c. So this is actually our y prediction. The y prediction, that is predicted value of predicted rating of moon on Uchi. So instead of that, if we can rewrite this one as m, instead of m1, we can think about like this is theta1, uh, and x1, and plus of theta2. This is another uh, theta2, x2. Okay, and plus of the c. Okay, the c, the c, uh, the c. We can consider this one is actually, we can see that there is our x0. Okay, x0, and so on that case, uh, we can represent this as the form like, uh, if we can consider there is the m, those values are in a vector. There is slope vector. The slope vector is theta, theta. Okay, the slope vector is theta, and this theta is specifically we're thinking about only the this user, that is the moon. So theta for moon. Okay, theta for moon. Uh, theta for moon. This is actually what this is actually. We have theta 1 and theta 2, theta 1 and theta 2. We can consider also theta 0 because we can see that if we consider our that is intercept vector, additional extra feature, that is x1 equal always 1. On that case, we can consider theta 0. The theta 0 maybe will always be 0. And our x is our feature vector for the for our that is our movie, that is Uchi, WOOCSI. So it will be again on that case we have like 1 and 1.0 and 1 point sorry 0.0.01. Okay, 0.0. Okay, so that means we can see now we can represent these things as just only theta transpose x. So theta transpose x, theta transpose x. So we will find out the values specifically theta transpose x. So that is our predicted value. But how can we find out the theta? What will be the optimal value of theta? So we know how to solve that. Okay, we know how to solve that because in linear regression we can apply the least square method. We can apply the gradient descent approach to find out the optimal value of theta, specifically here theta 0, theta 1, and theta 2. Oh, oh. So here is in case of the content-based recommendation systems, if we want to apply to find out those values using our gradient descent approach, then what we have to do, so we have to initialize the theta 1, theta 2 up to theta nu. So first the nu is the number of users in our case, okay? Number of users. That means we can say uh, not only the moon, we can also find out the for the Kim, we can also find out for the Lee, we can also find it for the Rim. So all these theta values we want to compute just maybe at a time, just one time. Okay, so for that we have different theta for Rim, theta for moon, theta for Kim, theta for Lee. Okay, that's why in this case we can see we can initialize theta 1 and theta 2. Theta 2 is our moon, theta 1 is what? Theta 1 is for the Rim. Uh, uh, so with the small random values. So initially, I think if you can remember the method we have uh, used for gradient descent and linear regression. Uh, uh, so on that case, what we have to do, we have to initialize the values of C and M. Okay, here is also the same thing. The C and M is specifically our thetas. We have to initialize with the random values and then learn theta by solving the following optimization objective. Here, optimization objective is the minimization. This is minimization over these terms, over this theta. That means we need to learn the theta, and for that, uh, what we need to find, what we need to maybe optimize. So we need to optimize this specifically theta j transpose xi. This is the predicted value minus this is the yij. This is originally value what we have already. So that means we can see these are actually these are already y. These are y. These are y already given. So that means those value already we got. So these are the y values, the actual values. Uh, so that means prediction minus actual. So this will give us what? Give us the residual. And then here is a square. There is a square residual. A square residual. And we have to sum up for all. That is sum of square residuals. Okay, sum of square residuals. Uh, and then we can see here this summation is actually R of I j equal 1. That means the rated movies only. Okay, so R of I j 1 if user j has a rated movie I. Okay, zero otherwise. Okay? And for that this is we will consider only rated movies, and for each and every user we can see user j to nu, that means for any user number of users we have from J1 to J U. So for all the users, we have to sum up these, and then this half is for mathematical benefit, as I think um, you know about, because we will try to find out the gradient, and if we take the derivative of this equation with respect to theta, then here is the two. This two, it will come in front of this equation. So on that case, half and two will be cancelled out. Okay, that's the mathematical benefit. Actually, that's here. That means we can see this is actually the derivative with respect to theta. If we take the derivative with respect to theta, then we will get this. And another term here is this is called the regularization term. Okay? Regularization term. In least square method, we have some sort of biasness, and that's why usually we use also the regularization, the lambda by 2, and then the summation of uh, k equal 1 to n. Here is the theta of k. That means for all the theta we have squared that, and this term is actually for the regularization. Okay, for the regularization. If we can remember about the Ridge regression, then I think you are already familiar with that. And so to find out the solution using the gradient descent approach, we have to take the derivative of this equation with respect to theta. So if we take the derivative with respect to theta, then we will get this. Specifically, we will get this value. We'll get this value. Okay, this value. But when k equals 0, that means the iteration 0. Initially, we have to assign initialize those values as those values with random, small random variable values. Okay, and for that case, initially no need to regularize. Okay, no need to regularize. So that regularization part is not here in k equals 0. So the regularization will be there when k equal 1. Specifically, we can see that this is k equal 1. It will start from k equal 1. So here for that case, and for other k, we will get this equation. Okay, using this equation, at first we need to find out maybe the theta initially, and then in next iteration, we will that is update the theta by these equations. Okay, by these equations, and maybe after many iterations, what we will get the stable theta and k. The k will not, the theta will not change very much. Okay, so or maybe you can say we will iterate this one up to 1,000 iteration, and after that we will get the optimal value of near optimal value of theta. And if we get the theta, that is theta, then we can easily find out the prediction. Okay, as I already mentioned here, if we know the theta value, then we can easily find out the predicted value. The theta means theta 0, theta 1, and theta 2. Then if for any new movies also, if we know the feature values, then we can easily find out the predicted values on that case. Like a new movie, maybe you can say the Gladiator is there. Okay, and we know that there is the feature values there. Mostly that one is kind of the action, maybe 0.8, and there are also the romance in that is the 0.2. Then what will be the predicted values for that? If we consider for the moon, on that case, maybe for the Gladiator movie, what will be the value of that? And we know that the theta, there is theta 0, theta 1, and theta 2. Theta 0, theta 1, and theta 2, it is maybe you can say 0, 5, and 0. Okay, 0, 5, and 0. So this is we have already learned from this uh, from this that is the gradient descent method. And then we can predict the ratings for the Gladiator in case of our that is the moon, for the user moon. On that case, just theta transpose x. So theta transpose x, theta, these are the theta values. These are the theta values. And the x value is this 0.2 and maybe 0.8. And on that case, we can see the prediction will be theta 0 is 0, and then x1 theta 0 with x0. X0 is you can say 1 plus of then theta 1 is 5, and x1 is, we can see we have x1 feature value for x is zero point 0.2 maybe, yes, zero point 0.2 plus, and then uh, theta 2 is what? Theta 2 is 0 uh, times our x2 is zero point 0.8, so x2 is 0.8. So the predicted values will be, here is 0, here is 0, 0.5 times 2, that is, we can say 1. Okay, so the predicted uh, values will be 1. Okay, uh, the predicted rating will be 1, that is 5 times zero point 0.2 is 1. So this is how we can apply the linear regression also, specifically finding out the regression parameters using the gradient descent, and use that values to find out the predicted ratings. And if the predicted ratings are high or maybe greater than uh, a threshold, then we can maybe recommend that movie to that user. Okay, so that's our content-based approach. Now, I think it's time to discuss about the collaborative filtering, the uh, another recommendation systems. So in collaborative filtering, what's the major thing we need to think about here? Um, so in collaborative filtering, actually, uh, there are two types of collaborative filtering approach. One is called the user to user, another is called item to item. Okay. Think about the collaborative filtering is our user to user mechanism. Okay? User to user. It means we need to find out the user of similar minded user, similar minded user. Uh, so similar minded, it means the likely minded users. So we need to find out the likely minded users. That is uh, uh, the same behavior or same mentality users you need to find out, and based on those users rating, we will try to predict the rating of you. Okay, because those are similar minded people, so maybe if they like one thing, then it is highly likely that you also like that item. Okay, so that's the intention here. That's the intention here. So that's why find set n of other users whose rating are similar to X ratings. Uh, so we can see that maybe this is you, this is here, this is user you, and you prefer something. Okay, and also we can say these are the other people, those are also uh, prefer the same thing. Okay, prefer the same thing. That means they're kind of, we can say that those you and those people are actually similar minded, because you have similar choices. Okay, similar choices, you have the similar choices. So that's why find n of other users whose rating are similar to x's rating. X is this user, x's rating. Then estimate x's rating based on the ratings of user in n. So now we can say this user search in a database, and we can see that is these users prefer, like maybe you can say these items. Okay, these items. So these users preferred these items. So then it is most likely that you also prefer those items. So that's why we can recommend you those items also. Okay, so that means based on your preference, we need to find out the similar minded people. That means those ratings are on this item, maybe the same kind of rating. And then uh, we will see that, we can see that maybe these users like this item. So based on that liking, we can also recommend that, or we can also assume that you also like those items. Yeah, so that's why we will recommend that items to you. So that is called collaborative filtering. So now, again, we can see that we have to find out the similar-minded people. The similar-minded, that means we can say we have to apply some sort of similarity measurement here. And for the similarity measurement, there are several metrics, and I have already discussed about the cosine similarity. So I think no need to discuss it again. Cosine similarity between XR and XY. So ratings of X and ratings of maybe Y, the other users. Uh, and another thing is we can consider about the Zakat similarity. So Zakat similarity. So we will explain this one, the Zakat similarity, maybe later, and the Zakat similarity measurement. Okay, we can apply the Zakat similarity measurement also. And then cosine similarity we have already discussed. And another one is called the Pearson correlation coefficient. Okay, this is kind of the similarity also. But we can see here that is in that case there is R of, we can say, uh, S and XY items rated by both user X and Y. Okay, items are rated by both user X and Y. So here this is the rating, and this is the average rating of X. That is this, we have to subtract that, and this is the rating, but we have to subtract the rating of Y from that. Okay, rating of Y from that. So here user X and user Y. So this is actually the rating of user X, and we have to subtract that one, subtract the mean rating from user X, of user X. And then this is the rating of Y, and we have to subtract uh, the mean rating of Y from that. And then we can see, um, actually this vector and that vector, this vector and that vector, you can see those are the vectors. We have to find out the length of those vectors. Okay, the length of those vectors. Okay, the length of those vectors. Actually, the same thing here. We can see it is kind of this kind of our cosine similarity. That is the denominator term. This term. Instead of Rx and Ry, we have to find out the length of the vector. That is the norm 2 of Rx minus Rx square and Rys minus Ry square. Okay. So that will provide us the correlation coefficient. Okay, correlation coefficient, that is the kind of the similarity. Uh, so let's say we have A, B, C, and D, those four users, and we can say these are the movies like the Harry Potter 1, Harry Potter 2, Harry Potter 3, Twilight, and maybe SW1, SW2, and SW3. Um, it is Star Wars 1, Star Wars 2, and Star Wars 3. Okay, so those are the movies. Uh, that is the Harry Potter 1, 2, 3, and Twilight, and that is Star Wars 1, Star Wars 2, and 3. So those are the movies. And we have, maybe we can say we have A, B, C, and D for uh, users, for customers. And the ratings for A on the Harry Potter 1 is 4, and like this way. Okay, so these are the ratings. And then in case of our collaborative filtering, what we have to do, we have to find out the similar-minded people. Okay, similar-minded people. Then similar-minded people, it means we have to find out the similarity between, maybe you can say AB, and maybe you can say AC. Okay, let's say we want to find out the similar-minded people of A. On that case, maybe AB or maybe AC and AD. Okay, like this. So for that, we can apply any kind of similarity function, okay, like the cosine similarity or maybe Jaccard similarity also. The Jaccard similarity, I think we have another lecture, another. For the Jaccard similarity, I think it's better if we can discuss from here. Okay, the Jaccard similarity specifically the Jaccard similarity. Then from the similarity, we can find out the distance. If we consider about similarity between these two sets, then Jaccard similarity, what it will do, it will try to find out the intersection between these two and divided by the union of these two. Okay, so if we consider this one is our C1 and this one is our C2, then if we intersect between these two, then we can see this is the intersection zone. And in this zone, how many we have? Just maybe you can say three intersections. So three intersections. And then here's the union of these two. That means we have total 1, 2, 3, 4, 5, 6, 7, 8. So in union, we have 8 instances. Okay. Now the Jaccard similarity will be the intersection by union. Okay. So intersection is 3 intersection elements. Those are 3, and union is 8. Okay. Union is 8. So this is called the Jaccard similarity. Jaccard similarity 3 by 8. And then what will be the Jaccard distance? It is 1 minus the similarity. Okay, 1 minus the similarity. It is 1 minus the 3 by 8, that is the 5 by 8. So this is the Jaccard distance. So we can find out the Jaccard similarity. Maybe you can see here. If we think about like how to compute the Jaccard similarity between we can say we want to find out whether similarity between AB is greater than similarity between AC or not. Similarity between AB using the Jaccard similarity, it will be, we can see AB. Okay, so that means these two instance. If we think about our union, okay, union, then sorry, if we think about our intersection, that means the ratings we have in both of the A and B. You can see here on that case how many times we got that. So this is one time we can see actually we we got the uh, mm, our ratings from both A and B just only one time. Okay, one time. So uh, that is our intersection. The intersection is 1. And how about the union? The union on that case, we can say this is one time, and this is another time, this is another time 3. There is the 4 and 5. Total, we can see 1, 2, 3, 4, 5. So total 5 times we got the uh, ratings. Okay, total 5 times we got the ratings from A and B. So this is called the Jaccard similarity between A and B. Then we need to find out the Jaccard similarity between A and C. If we consider A and C, so that means on that case, think about this one, and the C is that one. Okay, on that case, you can see there is how many times we got the result, got the ratings in both of A and C. So the both A and C, this is one time, and then another time is this. That is the 2 times. Okay, so that means the intersection, it will be 2 divided by, and now total number just only you can say the where we got the ratings between A and B, that is our union. So on that case for the A, this is one time here, and then maybe this one 2, this one is 3, and here is the 4. Okay, so that means total, if we union that, we will get the 4. So here is the 2 by 4. So Jaccard similarity, it will be 2 by 4 here. So now we can see specifically 1 by 5 is less than 2 by 4. Okay, so the similarity between A and B and A and C, if we measure, then using the Jaccard similarity, we will find out that the C is more similar than the A, than the B to A. Okay. Um, uh, But sometimes maybe we can use the cosine similarity. If we apply the cosine similarity between those, then we can see if we will get the reverse result here. Okay, the reverse result. On that case, the similarity between A and B will be high than the similarity between A and C. On that case, you can see applying the cosine similarity, we will get B as the neighbor. Okay, as the neighbor, the nearest neighbor A. Um, but now we can think about like specifically if we utilize these ratings, maybe we can get some biasness. Biasness. What's the biasness here? The biasness is uh, some of the users. We can say maybe those are our high raters. Okay, we can say high raters. Okay, high raters. Uh, So usually uh, they rate always with higher values. Okay, and some of the raters maybe we can say that those are hard raters. Uh, the high raters we can say that those are easy raters. But some of the raters maybe those are just hard raters. Hard raters mean the tendency for them is to rate using the low values. Okay, so this is uh, kind of the biasness because we can see that maybe their ratings for those hard raters, uh, maybe their standard value out of 5 will the maximum maybe 3, uh, 2 or maybe 1 within this range they rate like 2 3 1. But for the high raters usually they start the rating from maybe 4, like 4 and 5 will be their ratings. Okay, so on that case we can see there is the kind of biasness based on people's behavior and rating. So we want to omit those kind of biasness. Then what should we do? On that case, uh, subtract the row mean. Okay, so that means we have to subtract the mean value from each and every uh, number, each and every number. We want to subtract the mean values from each and every number. Okay, let me clear this one. Okay, it means that so this is a row. Okay, this is A is the row. The mean value we want to find out the mean for that. That is the 4, 5, and 1. What's the mean for that? The mean value. It is 4 plus 5 plus 1. That means we can say 5 plus 5 is 10. 10 by what? 10 by 1, 2, 3. Okay, 10 by 3. So this is the mean, 10 by 3. Mean for the row A. So mean for the row A. Uh, Similarly, mean for the row B, we have to calculate the mean for the row B. Sorry, this is the row B. The mean value will be 5 and 5, that is 10 plus 14. This is 14. 14 by total 3. 1, 2, 3. 3 lets we have. That is 3. Okay. So mean for row A is 10 by 3. So what we have to do, we have to subtract the mean from each and every number. So like the 4 minus the mean, we have to subtract the mean. Mean is 10 by 3. 10 by 3. If we subtract this, there is 10 by 3. Then usually we get 3 times 4 is 12. 12 minus 10 is 2. Okay, so that means 2 by 3. We will get 2 by 3. And we can see this 2 by 3 is here. Here is the 2 by 3. Okay? After means subtraction. Similarly, there is 5. Here 5 after means subtraction, that is 10 by 3. It will be 15 minus 10, that is 5 by 3. 5 by 3. So here is the 5 by 3. And this is 1. Okay, so 1 by 1 minus 10 by 3. It will be 3 minus 10, that is negative 7. So negative 7 by 3. So here is the negative 7 by 3. Okay. So similarly, we have to subtract 14 by 3 from 5. Then we will get 1 by 3. And then 1 by 3, then negative 2 by 3. If you closely observe, actually, we can say that the summation of each and every row will be 0. Okay, will be 0. Summation of every row will be 0 in that case. Okay. So that means this is the mean subtraction. After mean subtraction, if we calculate the cosine similarity or Zakat similarity, then that will be good. That is there will be no bias of the hard raters or maybe the, the easy raters or high raters. Okay, so that kind of bias will be gone. Okay, so that means this is kind of the similarity measurement method we can find out from the similarity metric to recommendations. Now if we want to recommend, there is prediction of item S of user X. Okay, that is we want to find out the prediction of item S for the user X. Okay, and for that case, there is we have to predict the rating. That is rating of user X on the item I. On that case, we can see there is R of yi, R of yi. So here ratings of user y on I, user y on I. So this is user X and this is user y, and we can see there is y is the subset of n. So how can we determine the subset? This subset again, you can see that is maybe we want to find out the similar-minded user, but similar-minded k users only. Okay, k users only. That is from our total n users, we want to find out the k users using the similarity measurement. At first, we need to find out the similarity between x and y. Okay, like here, the similarity between A and B, similarity between A and C, similarity between A and D. And then based on those similarity, we want to find out the ratings for maybe this one. That is ratings of A on the ASP2, that is Harry Potter 2. Harry Potter 2, we want to find out that. And for that, the easiest method is this one. Uh, we have to find out the similar-minded people. So maybe we can say the similar-minded people. In this case, maybe we will get the B is the similar-minded people. Okay, or maybe the B and D are the similar-minded people. Okay, so then what we have to do, we have to sum up the ratings of those those similar-minded people. That is B and D. Okay, B and D. The similar-minded people, maybe we can say if we consider B and D are similar-minded people, then the ratings of B is 5 and ratings of D is 3 on Harry Potter 2. This movie, Harry Potter 2. On that case, we can see the average rating will be the 5 plus 3. So this one divided by the K, that is the value of K. We consider the K equal 2 here. So 2, that means it is 5 plus 3 is 4. Okay, 4. Similarly, if we think about our weighted method, that is, instead of just maybe averaging, we want to consider also the weight. And then on that case, we have to find out that is the five, not only the five times the similarity between A and B, the similarity value, okay, plus maybe the similarity is 0.9 or something if you consider this, okay, plus of that is three times the similarity uh, uh, between A and D, that is maybe we can say we can consider this one as just 0.2, okay, and then we have to divide this one by here you can see similarity, this is the similarity between X and Y for all Y. Similarity between X and Y, the summation is 0.9 plus 0.2. So then we will get the rating for that. Okay, we will get the ratings for that. So this is how we can find out the ratings, find out the ratings of this. But now we can see that is actually we don't need the features here. In case of our collaborative filtering, we don't need to know the features, okay, the similar features. We don't need to find out the feature of each and every movies. Like in our previous example, uh, in our content-based recommendation systems, we can see that we need the features, okay, feature of each and every movie. But in case of the collaborative filtering, uh, we don't need uh, actually the feature of each and every movie here. So this is good, one of the good thing in collaborative filtering. Now what we have discussed so far, that is called the user-to-user collaborative filter. That means we have to find out the similar-minded users. But the collaborative filtering can be item-to-item also. That is, we have to find out the item-to-item similarity. Okay? Item-to-item similarity. But actually, this similarity matrix, again, we don't want to uh, find out the feature values again. Okay, this similarity values, actually we want to find out the rating similarity, similar rating similarity. So like in the case of the item to item, here is, you can say these are the movies and you can say these are the users, okay, and the blank space, those are unknown rating, and we can say the yellow spaces already have the rating between 1 to 5. So those are the ratings of uh, different users to different movies. Now we want to estimate the predicted rating for user 5 on movie number 1. So this one we want to find out. Again, in this case, we want to apply the item to item collaborative filtering. Okay, item to item collaborative filter. And for that, what we have to do, we have to find out the item similarity based on ratings. Okay, item similarity based on ratings. Specifically, we can see this is 1, and this is 2, this is 3, this is 4, 5. So what we want to find out? We want to find out, that is, what will be the rating here for this user, okay, for this user and for this movie, what will be the rating for that? Then in case of the item to item similarity, that means we want to predict the rating of this item for this user, okay. So we have to find out the similarity between the items based on the ratings. That is, the ratings are given. So if we measure the similarity between one, this is one similarity between one and other movies, okay, other movies or other items, then one and one, the similarity, it will be one, okay, then because the same set, and then we can see that is for the two. We have to find out the similarity between 1 and 2 here. This one, you will get that. and then maybe 3 is that, 4 is that, 5 is that, and 6 is that. These are the similarities. Okay, these are the similarities. So here, what we have applied, actually we have applied the cosine, the Pearson correlation as the similarity here. Okay? This similarity, those are actually the Pearson correlation similarity. Okay? The Pearson correlation, I think I have already mentioned, I already discussed about the Pearson correlation similarity here. Okay, this is the Pearson correlation similarity. I think you can find out that. So after that, what we have to do again, we want to find out the value of the item, the number of items. It's the same as the k equal to. That means similar two items. Okay, similar two items we want to find out. Based on that, the similar to the mostly similar item is 6, because the Pearson correlation similarity is 0.59. And another one is this one, 0.41. So that means we can say uh, these two we have to consider. Okay, we have to consider these two. So here we have already determined the similarity weights. We can say 0.41 and 0.59. 41 and 59, those are the similarity values. And now predict by taking the weighted average. Okay, so we can see that is, if we do the weighted average for that, then 0.41, so that 0.59, you can say 0.59, this is the 6, and the the similarity is 0.59. So 0.59 times what? Times the 3, this one, this value, plus of, and then 0.41 for the 3, and the rating for that is 2. Okay, 2, divided by, you can say, that is the similarity. So similarity is summation of the similarity 0.59 plus of 0.41, it is 2.6. So the ratings will be 2.6 on that case. Here is this predicted rating. Okay, so this is called the item to item similarity. uh, So we have already discussed about the collaborative filtering, and that is item to item similarity, item to item collaborative filtering, and user to user collaborative filtering. And we have already discussed about the content based uh, uh, approach. Um, but we have also the hybrid approach. Okay, the hybrid approach. Uh, Usually we apply the hybrid approach in many cases. Okay, in many cases, that means um, the kind of, we can say, the content based collaboration, content based recommendation, plus of our uh, there is a collaborative filtering based uh, uh, recommendation also we can combine to find out the rating. And one of the hybrid approach is called this one. Define similarity S of I j of items I and j. We already know that, and select k nearest neighbor. We can say we have already. We can select the k nearest neighbor, and then uh, the items most similar to I that was rated by X. Okay, and so estimate the rating as the weighted average. Okay, weighted average. So previously we can say we have this equation for that, that is the weighted average. So here is also the same thing. You can say this is S of ij, and this is also summation of S of ij, and here's the rating of X over j. But the new thing is this one. This is called baseline estimation of I, and here is the baseline estimation for j. Okay. Uh, Now we can say in this case, the baseline estimation for Ri, we can use this uh, method for the baseline estimation. There is the mu. Mu is the overall mean movie rating. So this movie rating actually considering the whole data set, overall mean movie rating, considering the whole data set where we have the rating, and then that means we have to think about like that is considering all those values. all those values, all those values. Uh, and then we can say all those values except the, the, the ROI, that means except this one. So we have to consider all those ratings, and that is called the average, okay, the baseline. So overall mean rating. Then we have the B of X. What's the B of X here? The B of X is rating deviation of user X. So rating deviation of user X, that is for a specific user, like here, we want to predict the value for this user, yeah, for this user file, for this user, for this user. Then the rating deviation, it will be the average rating of user X minus of mu. So average rating of user X, that means we can say, if we consider this user, then these are the values. These are the values. So what we have to do, we have to find out the average of that. So we have to find out the average of that. That is called average rating of user X minus the mu. We have already calculated the mu. So this is called the rating deviation of user X. Rating deviation of user X. Then rating deviation of movie I. We have to find out the rating deviation of movie I. So movie I, that means we can see for this movie, we want to find out the value. That is, we want to predict this value. So at first, we need to find out the average ratings of these movies, of this movie, the average rating of this movie. So that is our average, the average minus of mu. Then we have to again subtract the mu, the average rating of the movie I minus the overall mean movie rating. Okay, mean movie, that will be our PI. So if we add this one here to our R of xi, then we will get the predicted rating here. Okay? Predicted rating. Okay, so this is the hybrid approach. This is the hybrid approach. Traditionally, item to item and user to user for the case. Actually, item to item is better option rather than user to user. Okay, because we can say uh, actually the item to item similarity, those are more common and more justified process. The items are simpler, and the users have multiple tests. Maybe on the case, if we think about the user to user collaborative filtering, maybe user have multiple tests also, not only this kind of movie, they also like other kinds of movies. So that's why the similarity, user to user similarity, uh, it doesn't make sense that much as the item to item similarity makes sense. But the last thing I want to discuss in this here is that specifically we need to measure the similarity. But the measurement of the similarity, if we consider about the huge data set, that is too much complex for that. Okay, so that's why maybe for a small data set, we can think about like the Zakat similarity, cosine similarity. Those are very easy to find out. But if we have a large data set, then how can we find out the similarity? How can we find out? How can we measure the similarity for that case? And specifically, that one is deal by the locality sensitive hash. Okay, locality sensitive hash, the LSH. That means we will not consider, we will not there is the for measurement of similarity, like I have already discussed here. That is, if we want to find out the similar items of A, and if we have the data set, we have like the other users like B, maybe C and D, uh, B, C and D. So now what we have to do, we have to check the similarity between A and B, similarity between A and C, and similarity between A and D. If we can think about like we have like maybe 1 billion user internet we have, uh, then how can we measure similarity between those users? That is A to B, A to C. How can we find out the similarity? Okay, that's complex and that's not possible even in traditional method. So that's why we want to find out, that is, we want to find out the similarity. Those have some specific criteria. We don't want to consider all the users. We only consider some of the users. Those have some specific criteria. And then it will be easy for us to find out the similarity only between those users. Okay. Um, so here is in this lecture, we can see that is we need to find out maybe this image here in internet. The billions of images are there, but we want to find out the similar. But how can we find out the similar items there? Okay. Uh, so this is a problem of high dimensional problem. Uh, like if we consider this example, like image is a long vector of pixel colors. Okay, so even if we consider about this small image, that is a small image, those are just color values 1, 2, and 1. And if we vectorize it in one dimension, then 1 to 1 and 0 to 1 and then 1, 0, 1. Okay, so this is the vector. And some distance function. Now we want to, for finding out the similar items, or we can say, yeah, similar items, we have to apply either maybe the similarity function or maybe the distance function. But how to find out the distance or similarities? And maybe to find out the k number of similar items, we will apply some form of a threshold like S, the distance or a similarity less than that will be considered only. Okay. So this is if we try to find out the solution in naive approach, that means whatever we have done so far, it will take order of n square. Order of n square. The complexity will be for that. It is order of n square. So here, in this case, we can see that is if n is just 1 billion or something, that, actually it's not possible. But if we can apply some of the trick, then this problem we can solve within order of n. Okay, but how? And we need to find out that. Previously, when we have discussed about our actually the association rule mining, on that case we have already discussed about the PCY algorithm, the finding frequent pairs for that. Okay, and this is kind of we can say kind of the concept we have used about the hashing and bucketing. Okay, hashing and bucketing there. So if you want, then maybe just review that same thing here, because it will give you the base to understand our today's lecture uh, on hashing also. Okay, locality sensitive hashing. So first, the difference here, in previously we have in a priori algorithm, the main idea is to find out the candidate item sets. Instead of keeping a count of each pair, only keep a count on candidate pairs. Okay? The same thing in today's lecture also, find pairs similar, if we consider about similar documents we want to find out, then idea is the candidates. In pass one, take documents and hash them to a bucket such that the document that are similar hash to the same bucket. Okay, so that is the regular phenomenon in our hashing algorithm. And in pass two, only compare documents that are the candidates. Okay, that means that are on the same bucket. So we will try to find out the hash, and then the same documents, maybe it will get to the same bucket, and we will only determine the similarity on the bucketed elements. That means the element on that bucket. Okay, so that will provide us the benefit. Uh, now we can think about the Zakat similarity, or we can think about also our cosine similarity, or some other distance metric also. I have already discussed about the Zakat similarity from this slide to find out specifically the nearest neighbor. Okay, um, to find out the similar documents, specifically we need some sort of feature extraction methods, and one of the feature extraction method is called the shingling. The convert documents to a set. Okay, uh, but I have already discussed about the TF-ITF factorization, that can be also applicable here. Or shingling, if we can think about to find out the feature set, you can also learn about it. The shingling is very I think very easy approach to convert documents to a set to find out our some kind of feature factors. Like if we have a document that is called D1, D1, if we have the D1, and then in the document we have like the text are this A B C A B. Okay, uh, then if we want to find out the shingles of two items, okay, two items shingles, two items shingles, usually we call it K gram. Okay, K gram, K equal to 2 gram. So 2 gram, on that case, what will be the shingles for that? That is, the first shingle will be AB. Here is the AB, and then second shingle will be BC. Here is the BC, and third shingle will be CA. Here is the CA, and fourth shingle will be again the AB. But we can see AB is here, AB is there. So actually, in our shingles, we will get that is AB, BC, and CA. Okay, this is these are the shingles of D1. Okay, this is called the shingle. Shingle, that means K gram. K equal to, you can think about like 3 gram, 4 gram, 5 grams. Okay, uh, character samples. Okay, now what we want to do, those shingles, we want to apply some form of hashing for that. Okay, hash the shingles, this one, then maybe those values it will convert it to 1, and these values will convert it to 5, and these values will convert it to 7. uh, uh, so I think you know the hashing, that is hashing. Usually what it will do, whatever your value is, uh, like maybe you can say, if we think about uh, HE double LO hello, if we apply the hash function here, hash function, right, the h of something hash function, and then the output will be some of the values like maybe f 23159 something. Okay, and then if we apply again hello, just what, okay, not of exclamation, and again if we apply the hash function, and then it will maybe it will have different hash because this is actually different, so it will consider this one is f 3659592. That is the different value and different value. uh, uh, so different value. This is the cryptographic hashing. On that case, if we change something a little, then we will get the different hash. But now, actually, what we want, there is the instead of this kind of cryptographic hashing, those are actually present some the different hash values. But we want to check that these are the mostly similar text. Hello, and here is a hello heart, hello exclamation. So similar text, those will maybe those will be in the same bucket, or we can say kind of it will generate the same hash function. Okay, same hash function. But if we have the different something like word, if we hash it, then we will get the different values. but those are very similar. Actually, we want to get uh, those uh, those values in a single hash bucket. Okay, hash bucket. Or you can say we want to generate the same hash value. So here is a computation that is, if we want to find out the Jaccard similarity for pair, just pair of documents. Uh, so in this case, n times n, that is the possible number of pairs on that case, the comparisons, it will be n times n minus 1 divided by 2. So it will be like 5 times 10 to the power 11 comparisons are required uh, on that case. That is actually it can read like 10 to the power 5 seconds per day, and then it will take total 5 days just for generating the similarity. Okay, 5 days. So that is too much. Okay, so if we consider about the like n equal 10 million, then it will take more than a year just to find out the comparisons only, to find out the similarity, the Zakat similarity. So here, in case of our LHS, that is locality sensitive hashing, at first, for the document comparison, what we have to do, at first we have to generate the shingles. Shingles, as I already mentioned, this is kind of the features, okay? Kind of the features, and we already already have seen that those kind of features. And then what we have to do, we have to apply the mean hashing. The mean hashing, it will generate the signatures. Okay, generate the signatures. So that means after generating your features, we have to apply the mean hashing. If we want to find out the similarity specifically in our collaborative filtering approach, like we want to find out the similarity between A and B and A and C and A and D. Actually, the feature values are already there. Okay, so no need to think about the shingling in that case. That the feature values we will already get here. So the next thing what we have to do, we have to work from here. That is the mean hashing. We have to start from here, the mean hashing. Start from mean hashing. That means we have already the shingles uh, because the documents has the text. So that's why we need the feature, and shingling is one kind of the feature extraction method from the text. Okay, but in case of our collaborative filtering or content-based filtering, if we want to find out the similar items, on that case, actually, the feature values are already there. Okay, the feature values or ratings are already there. So no need to think about shingling. Just think about the mean hashing. We have to start from the mean hashing. So I think we have already discussed about the Zakat similarity and Zakat distance, how to compute that. Then it's better, I think, is if I can directly move how to find out the signature matrix. Okay, signature matrix using how to find out the mean hashing. After mean hashing, we will generate the signature matrix. Okay. So let's say this is our that is the shingling documents. Okay. Uh, what does it mean? It means that actually this is the document 1. This is our document 1, and this is document 2, and this is document 3, and this is document 4. And these are the singles. Okay, that means we can see, that means, okay, maybe in our single, some of the singles we can consider like SH. Maybe we can say the next single is TI, and next single is maybe ES, and maybe ED, and and maybe 3 singles are there also, like TIO and TION. and maybe AC. Right? So these are the singles. Okay, these are the singles. So that means actually in a documents, lots of singles can be. Okay, like billions of singles we can consider. So in this case, that is in document one, whether the is a single present or not. If it is present, then this is one. If it is not present, then just zero. Like SS single, SS single, that one is present in document one. That's why here is one. And SS single is not present in document two. That's why it is zero. And then this is one, this is zero, like this. Similarly, maybe you can say AC, this single present in document one, but absent in document two, present in document three, absent in document four. Okay, so that means these are the single documents. In our case, maybe you can say these are actually our that is movies and their the ratings of different users. Okay, different users. So on that case, what we have to do, we want to now generate the signature matrix, applying the mean hash, applying the mean hash. So for that, what we have to do, we have to generate the permutation. Okay. Uh, Initially, we can say this is this single. This is the we can consider this is one and this is two. This is two and this is three. The single number maybe four and five and then six, then seven, like this way. Okay, like this way. And then what we have to do, we have to think about the permutations. Okay, like the permutation of this. It means the just permutation of these shingles. So if we permute this one, then maybe you can say previously two, this one we will find in first position, one. So this is the permutation. Okay, this is the permutation. 2, 3, 7. That row number 7 is maybe shifted from last position to here, and then 6, then 1, 5, and 4. So these are just one permutation. So this permutation actually it can be generated from a hash function. The second permutation is again is kind of the other permutation. Okay, actually this one can be generated from the second hash function, and this is another permutation. This can be generated from the third permutation. Okay. Um, then from here, what we can do, what we can generate the signature matrix. Okay, signature matrix. Like from the first permutation, where is one? This is the one. This is the one. Okay, this is the one. And in that case, we can see there is this is one. Now from the one we can see here is one and here is also one. So we want to generate the signature matrix, and this one, that is the second position, and here is the fourth position, fourth position. And now these positions are fixed. Now we have to go to our that is the second position. This is second position. The second position two, we can see at first it is one, and in third position it is one. So that means we have to find out the first position and third position here. So first position one, that means here, and third position is one, that means here. Instead of one, what we have to write? We have to write this permutation value. That is the two. Here is two. Here is also two. So this is uh, a signature matrix. Okay, this is the signature. This is the signature for our first permutation. Similarly, if we consider about the second signature, we want to generate another signature for the another hash function. The hash function, it will return like this way. Okay, like this way. Um, so maybe you can say you can generate the hash function, and that hash function will generate these values. Or we can say just random shuffling those values. Then again, we can see here is at the first position. We have to check here. This is one. So here is one and here is one. So for the second symbol, for the second signature, The second position and fourth position is 1. And then we have to decide what will be in this position and that position. Okay. Now we can see we have to move to 2 here. This is 2. This is 2. So in this case, we can see that is first position is 1 and fourth position is 1. So first position is 1, the fourth position is 1, this 1 and first position is 1. That means in this position, uh, we can see the fourth position already. We can see we have the value that is the minimum, that is 1, and here is also 1. And then this value is what? This value is 2. Okay, this value is 2. Actually, this value is 2. So here we can write this 2, and we can write also here 2, but we will not write this 2 because this is mean hashing. So the minimum value we have to write. That is the previously we have the minimum one, so we will not update it. Okay. Then still we didn't have any value here. Okay, we didn't have any value in third position of the second signature. Then we have to check the third. That is, here is the 3. So 3 we can see here is 1. Here is also 1. So that means this 2 value is already there. So we will not update it. Then we have to move 4. Here is the 4. And 4, the first position is 1 and third position is 1. That means first position, this is 1 position and fourth position is 1. Now we can say that is first position, we have to add 4, but already 2 is there. So 2 will be the case. Okay, so 2, we have to consider the 2 here because 2 is the minimum one. So minimum 2 is there. But the third position, we didn't have any value, so we have to add the 4. Okay, we have to add the 4. So this is the generation of the second signature. So then we have to consider the third permutation. Again, we can say this is the 1. So here's first position and third position will be 1. So first position and third position will be 1. And then we have to move to the second, that is 2. So on that case, we can see that there is second position and fourth position is 1. So second position and fourth position, we didn't have any value, so we can add this 2 here. Okay, add this 2 here. There is 2, there is also 2. So this is how we can generate the signatures. Okay, this is how we can generate the signatures. So this is after mean hashing, we will get this. Now, so mean hashing, the last option is from the mean hashing. We will find out the locality sensitive hashing. Okay, locality sensitive hashing, and using the locality sensitive hashing, we will get the candidate pairs, and we will just find out the similarity on those candidate pairs. And how to do that? So in that case, that is, we have to divide the matrix, that is the signature matrix, into B bands, and each and every band we will have the R rows. Okay, R rows. So if we consider about that is the signature matrix. Okay, signature matrix, and this is our signature matrix. Like in previous case, we have this is signature matrix. Okay, this is signature matrix. Specifically, this is one signature, this is another signature, and this is another signature. So this is the first signature. Okay, first signature. This is, we can say, signature A. This is signature B, and this is signature C. Okay, signature C. Now what we can do? Maybe we can divide these signatures into 2 bands. Okay, 2 bands, B equal to. That means we have to divide these signatures into 2 bands. So like here, that means these are the B bands. So we can divide our signatures into just 2 bands, B equal to. And on that case, each and every band, we will have just maybe R rows, R number of rows per band. So in our case, like this one, we can say this is the signature A, this is the signature B, this is the signature C. And then if we think about, like, we will have in each band, we have divided this on 2 bands. then this part of the signature and this part of the signature. Okay, so we can see this is row number 1 and row number 2. So here is the row number 1 and row number 2, like this way. So that means it's kind of the transpose. Okay, so that means we have to write like 2, 1, 4, 1, and then 1 to the B signature B, 1, 2, then 1 and 2, and then third signature is 2, 1, and then 2, 1, like this. Okay, third signature is this. Now we have to think about, like, we have to divide it by B bands. So B bands is 2 bands. We want to find a 2 bands. Okay, so this is our signature A, and this is signature B, and this is signature C. So if we divide it 2 bands, that means we can say one band we will get these 2 rows, and another band we will get these 2 rows, and again these 2 rows and these 2 rows and these 2 rows and that 2 rows. Okay, we will get like this way. So that means we can say, like, here every band we will get like this is signature, part of signature A, this is part of signature maybe C, like this way. Okay, so now what we have to do, consider this signature and the part of it. Okay, and then apply some form of hash function, and this hash function, it will look at a bucket for that. And this is signature B, apply some form of hash function, it will also locate to a bucket. Okay, similarly the next part, apply the hash function, it will bucket, and B is apply hash function, it will be bucketed here. Apply hash function to another part, it will be bucketed here and bucketed there. But now we can see actually this one is on the same bucket. Okay, so this part and this part, that means on the same bucket. So that means we can see that we will only find the similarity between this one and that one. We will not compute the similarity between this value and this value. Okay, we will compute only the similarity between these two, because they are on the same bucket after the hashing. Okay, so there are several hash functions. We know this is one of the hash functions. We can say for I, j, and k, the value. There is I, p, j, k, and k are mod of m. P, q, and r, those are just maybe the prime numbers. Or maybe we can apply also this type of hashing also. Usually LSS also use the SSA 256, okay, the hashing mechanism, MD5. So there are several hashing we know about. So now what we can think about, like that is apply kind of the hashing, and if we get those are in the same block, then actually we will compare only those similarities. So other similarities we will not compare. So this is how we can that is for the big data, we can find out the similarity values. So I think we have to stop here. That's all in our today's lecture. The locality sensitive hashing and recommendation system, that was in our discussion today. So thanks everyone for joining here. I think we have to take the prayer break. Yeah, I think that's end of our today's class.
স্যার
Yes, please.
স্যার আমাদের তো নেক্সট ক্লাসে এক্সাম, তো আমাদের সিলেবাসটা কি লাস্ট ক্লাসে যেটা হয়েছে এন্ড আজকের ক্লাসের?
হ্যাঁ, আজকে ক্লাস পর্যন্ত আমি অ্যানাউন্স করে দিব।
স্যার আজকের ক্লাসটা কি রেকর্ড হয়েছে?
হ্যাঁ, রেকর্ড হয়েছে।
স্যার আমাদের প্রেজেন্টেশন কি হবে নাকি, মানে জানি না তো স্যার অ্যাকচুয়ালি।
আচ্ছা, আমি অ্যানাউন্স করব, আজকে চিন্তা করে অ্যানাউন্স করব, দেখা যাক কি করা যায়। হ্যাঁ,
ওকে স্যার, ঠিক আছে।
ঠিক
আর
আছে, ভালো
স্যার
থাকবেন।
আজকের রেকর্ডিংটা একটু যদি এখন শেয়ার করে দিতেন একটু ভালো হতো স্যার।
হ্যাঁ, আমি এই যে নামাজ থেকে এসেই শেয়ার করে দেবো। হ্যাঁ,
ওকে স্যার।
দেড়টায় জামাত তো। থ্যাংক ইউ। অ্যাটেন্ডেন্স সবার।